Howdy, and welcome back to ASTR 103 Astronomy Lecture 2 for our Astronomy series of Spring 2022. Today, the topic du jour is, I guess that's redundant, the topic du jour is astronomy and the size of the universe. And basically, I'm just going to briefly talk about what astronomy covers and spend the remaining portion of the lecture just talking about the sheer scale of things, both from a spatial scale to a temporal scale near the end. And when we talk about these things, for the most part, we're talking about really incomprehensible sizes, going down from the atomic level all the way up to the galactic or even supergalactic universal level. But I'm going to try to give you a few tricks or a few ways to make these numbers or make these concepts a little more comprehensible than they are on the surface. See if I can tech right today. Excellent. So, if you have not seen this picture before, it is fairly iconic in that it was taken on December 24th, 1968. It was one of the photographs taken by Apollo 8, the Lunar Reconnaissance Orbiter. And it is affectionately known as Earthrise. Although in later lectures we're going to find that Earthrise is something of a misnomer in the sense that the Earth does not rise and set in the traditional way on the Moon. This was a serendipitous discovery because essentially this was the fourth and last orbit that orbiter, that Apollo 8, did on that flight. And they had not seen the Earth through their viewports during the first three orbits, and they only caught this basically at the last second. And they scrambled to take as many photographs as they could with this. This is a color enhancement, shall we say, of the original. Actually, no, let me back that up. It is an enhancement, but I believe the first one, the originals were in fact in color. But this shows you a scale of this would be pretty much the closest astronomical scale, or the smallest astronomical scale that we're going to be talking about, the distance between the Earth and the Moon. And already you can see that the entirety of the Earth is small. It is far smaller than we see in everyday life. Even in aircraft, we don't see the Earth that small. And so when we start talking about larger and larger scales, keep this picture in mind as it really informs as to how large or how, well, I would say significant, but that's a loaded term, just how small we are in the grand scheme of the universe. Now, what is astronomy? I'd like to argue that astronomy is one, if not the oldest science in human civilization. Broadly speaking, astronomy deals with everything in the night sky and beyond. Astronomy deals with the stars as they appear, the planets, the moons, the stars where they're actually located, the lifetimes of these stars, nebulae, galaxies, and so much more. It details all of the physical processes which go on essentially outside of the Earth's domain. Now, I refer to it as one of the oldest, if not the oldest, science, because astronomy was used by ancient cultures well before documented evidence for, say, chemistry or biology, arguably physics, although there's some question there. The caveat is, of course, mathematics. Mathematics may, in fact, be the first true science. But regardless, astronomy has been with the humans for as long as they've been plowing into the earth trying to raise crops, because astronomy was primarily used for that purpose. That and astrology, which we really won't get into, but knowing where the stars are positioned, particularly knowing where the Earth and the Sun and the stars all lie within relation to each other, that allowed the ancient peoples to, at least to first order, know what season they were in. And so that dictated things like planting crops, harvesting crops, that sort of thing. And so by understanding when the vernal equinoxes, the summer solstice, the autumnal equinox, and so forth, they could understand the nature of the Earth and its cyclic processes. So, let's get into numbers, both big and small. Now, I'm going to try to make this as interesting as possible, although it's going to be, I will admit, it is going to be a little dry. But let's talk about scientific notation. Now, scientific notation is a shorthand, as it were, to, well, it's a way of expressing very, very small numbers. Well, let me back way off that. It is simply a way of expressing numbers. Now, it was primarily motivated, its creation was primarily motivated to properly, what's the word I'm looking for, show, lack of a better term, small or large numbers, incredibly small or incredibly large numbers. When you're talking about, say, for example, a billion, you have 1 and 9 zeros. So rather than put 1 and 9 zeros, you could put that 1 billion into scientific notation. Now, what is scientific notation? Scientific notation at its heart is a coefficient times 10 raised to an exponent. So 1 billion, for example, A would be 1, and B would be 9. So it would be written as 1 times 10 to the 9th power. Coefficient, in order to properly express scientific notation, well, properly, a coefficient must be between 1 and 10. So 0.5 would not be appropriate, neither would 11. Well, really, I need to edit the slide. 9.99 repeating. 10 itself would actually not be an appropriate number. So essentially everything between 1 and up to but not including 10. 11 would not be an appropriate coefficient. 100 would not be an appropriate coefficient. And then you have an integer, which can be positive or negative, ranging from negative infinity to positive infinity. A positive exponent means that you are multiplying the number by that factor, 10 raised to some positive exponent, 10 to the 2, 10 to the 5, 10 to the 100, so forth and so on. And what that really means is that you're moving the decimal over to the right-hand side. Let's return to our example of 1 billion. It's 1, comma, and then 9 zeros. So let's take that comma, and if we move it, we can move it 9 spaces to the, let me flip that on its head. You have 1, comma, 9 zeros, and a decimal point. In order to put that in scientific notation, you take that decimal point, you move it to the right, or to the left, really, 9 times, and that gives you 1 point times 10 to the 9th. 100. You move that decimal point over to the left by 2. 1 times 10 to the 2nd. A negative exponent means that you are shifting the exponent to the decimal place to the other side. So 0.045, for example, you move that decimal place over to the right twice, and you get 4.5 times 10 to the negative second. Or if it were 0.0045, you would get 4.5 times 10 to the negative 4, and so on. And so these units, these numbers can run the gamut of all numbers that you can think of. At least all rational numbers that you can think of. In terms of identifying what these are, and when I teach laboratories, or when I teach labs, excuse me, I cannot stress units enough. It may seem pretty, I'm just losing words left and right, pretty pedestrian to think about units. Like, who cares if it's in inches or what have you? Well, we've had real-world implications for units not working, or for people who have not paid close enough attention to units, ruining multi-million-dollar projects. The most obvious example that comes to mind, or probably the most infamous example, is the the British Mars satellite known as the Beagle, and this was going to be, I believe, a orbiter, a satellite that would orbit Mars. In any event, because the units were not paid attention to when they designed the thing, they were going from, someone had put the units from in metric or in meters, and the person who was building put them in imperial units, inches, feet, that sort of thing. And so obviously something was built incorrectly, and that particular mission smashed on the surface of Mars, and the scar of that can still be seen to this day. So there are many different types of units, and some of them are international. The imperial units are what the Americans use. It's what the UK uses. That's feet, inches, yards, so forth and so on. We will be using a system of units known as the MKS system, or meters, kilograms, seconds. All of our units are going to either be expressed in terms of meters, kilograms, or second, or some combination of the three. So obviously length is in meters. Velocity is going to be in meters per second. And weight is going to be in kilograms. Force is going to be a Newton, or a kilogram times a meter per second divided by a second squared. That's it, or that sort of thing. Now, when we use these particular units, we have certain prefixes, which is a shorthand for scientific notation. You're more than likely familiar with these terms in regards to computer software, or computer hardware, excuse me. For example, giga. We've all heard of gigabytes. We've all heard of megabytes. Giga is simply the prefix for a billion. So 1 gigabyte is 1 billion bytes. A megabyte is 1 million bytes. Then you've got kilo, or kilobyte, then centi, milli, and micro. One other prefix that I would like to mention that's not on this table is nano. Nano is the next one down, and that is 10 to the negative 9. When we think about light, particularly the visible portion of light, the nanometer is what we use to identify the range, or characterize the range, because it usually goes from, or typical visual range goes from about 400 to 750 nanometers. Again, 1 over 1 billionth of a meter. Now, if you want to take two different numbers that are written in scientific notation and you want to manipulate them, meaning that you want to multiply or divide them, or eventually either add or subtract them, this is how you would do it. So if you wanted to multiply two numbers, say 6 times 10 to the 3 and 2 times 10 to the 2, and you wanted to find out what those two values equal to, or equate to, is basically you're going to separate the coefficients and the 10 to the power of what have you off to the sides, and you're going to multiply all that together. So first you multiply your coefficients. You got 6 times 2, that's 12. Then you deal with the powers of 10. 10 to the 3 times 10 to the second is 10 to the 5th. And so you have 12 times 10 to the 5th, or again, remember, the coefficient for the scientific notation must be below 10 and greater than 1. So 12 is an improper way of expressing scientific notation, so you need to move the decimal place over to the left by 1, and that increases the exponent by 1. So 12 times 10 to the 5th becomes 1.2 times 10 to the 6th. Easy peasy. When dividing, you essentially do the same thing, although, so you'll group these. Let's take the same two numbers, 6 times 10 to the 3rd and 2 times 10 to the 10th, 2 times 10 to the 2nd. You would take 6 and 2 and divide those two. So 6 divided by 2 gives you 3. And then you would take 10 to the 3rd divided by 10 to the 2nd, and that would give you 10 to the 1st. So 3 times 10 to the 1st, or 30. Now, when you are dealing with addition and subtraction, what you need to do is get the powers of 10 in the same power. For example, you have 4 times 10 to the 3 plus 2 times 10 to the 2nd. These are you have 1 in 10 to the 3 and you have 1 10 to the 2nd. Those need to be in the same. And so what we're going to do is we're going to take the second value and change it from 2 times 10 to the 2nd to 0.2 times 10 to the 3rd. We have moved the decimal place to the left. That increases or increments the exponent by 1. Then you add those two numbers together, add the coefficients together, you get 4.2 times 10 to the 3rd. Now, another way of doing it, a longer way of doing it, is you could do the opposite. You could do 40 times 10 to the 10 to the 2nd. Then you add 40 and 0.2. Did I do that right? I don't think I did that right. No. You did 40 plus 2, and that gives you 42 times 10 to the 2nd. And then you'd have to move the decimal place over to the right, or over to the left, excuse me, and you get 4.2 times 10 to the 3rd. Again, you'd have to increment. I would go with the example listed. That is the easier and more, I think, the clear-cut way of doing it. But technically speaking, you can do it either way. More importantly to astronomers is something referred to as orders of magnitude. Now, you'll often hear, if you hang out with astronomers, you'll often hear the phrase, it's good to within an order of magnitude, meaning it's a fairly rough guess. Meaning that it is somewhere in a multiple of 10. So it could be 3 times, your guess could be 3 times or 3 times larger than the true value, or 4 times larger, or something like that. It's all within the same order of magnitude. And when you're dealing with such large numbers or small numbers, an order of magnitude is a fairly rough estimate, particularly given the error bars that we often deal with. Powers of 10, another way of thinking of orders of magnitude is powers of 10. And so for example, let's compare two values. 10 to the 4 to 10 to the 3. 10 to the 4 is 10 times larger than 10 to the 3, meaning that 10 to the 4th is 1 order of magnitude larger than 10 to the 3rd. If you were to compare 10 to the 4th to 10 to the 2nd, 10 to the 4th is now 100 times larger, or 2 orders of magnitude larger. To get an idea, when you see a number, to get an idea of what order of magnitude it happens to be, you just kind of round off, take the coefficient, round it either up to 10 or down to 1, and the exponent then gives you your order of magnitude. So 780, you round it up to 1,000, that's 10 to the 3rd. It's basically 3 orders of magnitude. 8.9 times 10 to the 6th becomes 10 times 10 to the 6th, or 10 to the 7th. Again, 7 orders of magnitude, or 4 orders of magnitude larger than the previous example, and so forth. Now let's talk about distance and time in the universe. I'm actually going to skip over this. If you are interested in learning how to convert units, we're not really going to be doing this too terribly much. And when we do this, I will be guiding people through this more step by step. But ultimately, what you can do is you can convert units in order to move from, say, miles to AU, or excuse me, meters to astronomical units to light years and so forth. But let's talk about measurements of distance. We have developed a couple of different meter sticks, as it were, in terms of measuring distance and having them be manageable numbers, or at least more manageable than not. So, for example, the Earth, if we were just to keep things in kilometers, the distance between the Earth and the Sun is 1.47 times 10 to the, I believe that's 8, sorry. 1.47 times 10 to the 8th kilometers, or 147 million kilometers. That is a mouthful. That is a very large number. So astronomers, and that's just the Earth to the Sun. That's not, say, the Sun to Pluto, for example, which is 40 times larger. So you'd have to do 40 times 1.47 times 10 to the 8th, and who wants to be bothered by that? So astronomers, being, somewhat lazy, have decided, let's make it simpler. Let us take the average distance from the Earth to the Sun and call it 1. And let's call that unit an astronomical unit, because we are so good at naming things. So very original. So 1 astronomical unit is the average distance between the Sun and the Earth. So now the distances in the solar system, at least, are much more manageable. From the distance from one of the Earth or Sun to the Earth, 1. The distance from Earth or Sun to Venus, 0.7. To Jupiter, 5, roughly. To Pluto, 40, roughly. Much easier. But unfortunately, that even astronomical units become clunky out to even stellar distances. So when we're talking about distances to other stars, now we're getting into, again, millions of AU, and we're back to where we started with in terms of measuring everything in kilometers. So what other benchmark can we use? Well, we know the speed of light has a constant speed in a vacuum, or space. So why don't we use the distance that light travels in a set amount of time? Now, the canonical way of doing it is a light year. How far does light travel in 1 year? And you can do the math, and basically 1 light year equals 9.5 times 10 to the 15th meters. Again, you can see why that's a kind of a mouthful. You don't really want to measure things in meters. The distance of the closest star is Proxima Centauri is around 4.5 light years. So much easier than 4.5 times 9.5 times 10 to the 15th meters. Another one, which is another unit that we use, which actually has its roots in one of the first techniques for determining distance, which we'll talk about later, is a parsec, or a parallactic angle of 1 second. Again, we'll get into that when we talk about trigonometric parallax. 1 parsec is equal to 3.26 light years. Now, in this course, I will probably keep to things in light years. When you get into astronomical papers, or if you're getting into astronomy, the more common unit is a parsec. So parsecs, kiloparsecs, megaparsecs, and so forth. Again, that is mainly because that is directly relatable to a distance measuring technique. So how do we measure the astronomical unit? Well, in the textbook, they give you a very good summary of how this was done. But ultimately, it boils down to measuring the transit of Venus across the sun at two different locations in the Earth. And you can use geometry based on where the eclipses appear on the surface of Venus. You can use geometry to determine what the distance between the Earth and the Sun is in absolute units or absolute numbers. Now, the certain ancient Greeks actually did not hold to the Aristotelian view of the geocentric universe and so forth, and they actually attempted to use different methods to calculate that same value, although they could only do it relatively, and the techniques they weren't great, and the numbers they were getting were far smaller than what we see today. They were far larger than what Aristotle and his ilk would have you believe, but they were not nearly accurate enough to get it. So the first reasonably accurate distance from the Earth to the Sun was done using the Venusian transits. Astronomers deal with things that are not only incredibly large, but incredibly small. And oddly enough, the folks that are primarily deal with things that are very, very small are the cosmologists. The ones that, the folks that are interested in the overall universe, how it began and how it evolves, so forth. They are the astronomers who are very interested in what the scale of matter and energy looks like on very small spatial scales. Because when you start talking about the Big Bang and the very early universe, you start getting down to these scales. And our understanding gets, kind of fuzzy in these points. And so when we're talking about scales, to give you an idea, the proton, the nucleus of the nucleus of the hydrogen atom is around 10 to the negative 15 meters. Or, to put it more easily, 15 orders of magnitude smaller than you. So, and remember, that is, every order of magnitude is basically a factor of 10. 10 to the negative 9 is a billion. So negative 15, I don't remember what the actual value or what the prefix is, but it's really, really small. When you get down to the orbits of protons or electrons around protons, then you start to get up to 10 to the negative 15 or 10 to the negative 10 meters. So 5 orders of magnitude larger than a proton. Now, something I get a kick out of when I think about things is if you were to look at the scale of, if you were to look at, say, the size of the sun and the earth and the magnitude or in the distance between them, and you were looking at their magnitudes, orders of magnitude, the order of magnitude between the sun and the earth and the sizes of the sun and the earth and their distance is smaller than the magnitude between the sizes of the proton and the electron and their distances. What this means is that everything that you see, all the matter that you see, in gases or what have you, are mostly nothing. There's mostly nothing there. The actual particles of matter are tiny with respect to how far away they are from each other. The only reason why we see things as solids is something of an illusion. Our eyes are just not sensitive enough, or they do not have the angular resolution enough to actually distinguish individual atoms, let alone individual particles within an atom. So what we're seeing is an illusion. What we see in our everyday lives is something of an illusion based on the limitation of the human eye. Then, of course, we have the mainstream, or most astronomy, deals with things on this size. So when we look at the universe, we go from relatively small to the solar system scale, up to, which is tens to hundreds of thousands of AU, out to the Oort cloud. Then we get into the Milky Way galaxy, which from end to end is roughly 100,000 light years. So now we've moved from AU to light years. Then we get to the local group. Local group is a small collection of galaxies, primarily 3 major ones that are all about the same size as the Milky Way, and about 24 smaller tiny galaxies that are currently getting eaten. And the size of that is on the order of millions of light years. Then you get to clusters or superclusters, which are hundreds, if not thousands, of these local groups. And then finally you get into these superclusters, the definite superclusters, the Lorca's, for example, and I'm pretty sure I'm butchering that name. These are millions of parsecs across, if not larger. So go from a few AU all the way up to millions of light years, millions upon millions of light years, or I guess billions of light years. So I've already talked about this as essentially increasing orders of magnitude. You can all the way go down to negative 15 for the size of protons and electrons, all the way up to positive 15, which is the size of stars. So there is basically 30 orders of magnitude between the smallest objects that we study and the largest single objects that we study, thereabouts. We are basically an order of the 0th order of magnitude, or 10 to the 0, our height. So if you're talking about the planets that orbit around stars, those can range from 10 to the 7th or 10 to the 8th. And it's an easy way of looking at it in the sense that those sizes are 7 or 8 orders of magnitude larger than you and I. I've listed a Powers of 10 video, a YouTube video. If you really like, shall we say, classic cinema, I'd highly recommend looking at that. That was old when I viewed it when I was in high school. That was from 1977. The graphics are they're just cutting edge. But it actually does hold up in giving you the basics idea and giving you a fairly good representation of what the difference between various orders of magnitude are. And then we get into, like I said, the biggest structures that we know of are galaxies and galactic clusters. You're ranging from they're 21 to 24 orders of magnitude larger than you or I. So now let's talk about the scale. Let's talk about something that is fairly commonly done, which is a scale model of the universe. Now, if you're interested in seeing one of these in real life, you can go to the mall in DC, and it's on the same side as Air and Space, and I think it starts about a block down towards the Capitol. And what they've done is that they've scaled the sun down to a particular size. I honestly don't remember what it is. And then they've scaled the distances to the planets and the planets themselves relative to the size they've shrunk down the sun to. And so you can literally walk the solar system. You can see on the scale just how close the inner worlds are and just how far away the outer planets get, particularly Uranus and Neptune. They are blocks down the line. But if you want to do it, if you wanted to do this in a different way, if you wanted to say use a scale model where it's 1 to 1 billion, meaning 1 meter equals 1 billion meters in real life, then the moon would be about a foot away from the Earth. The sun would be 1.5 football fields away from the Earth. And again, the Earth is the size of a marble in these terms. Neptune is 3 miles away, and the nearest star is the length of the circumference of the Earth's surface. So, and then beyond that, even on that scale, you start for Milky Way and the superclusters, you start getting into, again, astronomical scales, which are hard to conceptualize, even given this scale. So, I like to think of the Neptune example is the one that really drives it home to me, because this distance to Neptune I can kind of conceptualize. particularly if you tell me that the Earth is the size of a marble and it is 3 miles away. That gives you an idea. There's also a YouTube video, and I'll link it in the description of this, called the scale. I think it's the scale model of the solar system. It's these folks who, college students, I think, they go out to the Nevada desert and they actually create a scale model where I think it's roughly 1 to 1 billion. The Earth is literally the size of a marble, and they drive out 3 miles and place Neptune, and just the scale of it is amazing. They actually do a sound test to kind of illustrate that scale, because while the speed of light is very fast on a terrestrial scale, the speed of sound is not. And so they show you when they hit the air horn, and then you wait for when the air horn sound actually gets to Neptune. It's actually pretty cool. This is a simulation that I also put in the description. It is a computer applet. You can also find the link in the PowerPoint slides. This is a nice little computer simulation to, yet again, illustrate the various interactive simulations of the scale of the universe. Now, we've been concentrating primarily on the size scale, or the size scale, spatial scales of the universe, and just how mind-bogglingly large it is. But let us not discount just how mind-bogglingly old it is. The universe has been around for 13.8 billion years. It started off as in a region of space that was exceedingly tiny. It may not have been a singularity, it may not have been a point of no radius, but it was close. Depending on who you talk to, the size of the big t equals 0 differs. But then over 3 billion years, it has gotten ginormous. And so we can, by studying the universe, studying cosmology, we can see what the universe looks like at these various stages. Now, one of the ways, or really the primary way that this happens, is because of a really nifty consequence of the fact that the speed of light has a set speed. And it really gets you thinking, particularly if you're on certain, shall we say, medications, when you think about this for a moment. Now, terrestrially speaking, again, this is not really an effect that you notice. But when you get even out to astrophysical distances, like, for example, within our solar system, it takes light roughly about 8 minutes to go from the sun to the Earth. So if Thanos were to snap his fingers and turn the sun off, we wouldn't know that until 8 minutes later. We wouldn't know it gravitationally, we wouldn't know it electrostatically, we wouldn't know it optically or visually. We would have no way of knowing what the sun did, or that the sun was gone, until 8 minutes after the fact. So what we do, so astronomers, in a way, in a really rough way, can be thought of as time travelers, in the sense that the further out in space we look, the longer or the further back in time we are looking. Proxima Centauri, as I said before, is approximately 4 to 4.5 light years away, meaning that when we look at Proxima, we are looking at Proxima as it was 4 years ago. We are not looking at it as it is right now. When we look at the Andromeda Galaxy, we are looking at the Andromeda Galaxy as it was 2.7 million years ago. We are not looking at it as it is now. And so when we can look back to the basically the very visible parts of the galaxy, or very visible parts of the universe, and right now, optically, we only get to around a few billion years. So we haven't. So one of the things that the JWST, the new satellite that just went into orbit, we're hoping to be able to look even further and actually see galaxies that were, or what the universe looked like on timescales around a million years or so. the thing that twists my noodle is that you can go backwards on that mentality, in that nothing that you are seeing at the moment is what it is right now. Everything that you see around your room happened in the past. While we're talking nanoseconds, but it's still in the past because it still took light a certain amount of time to get from wherever it is you're looking to your eye. So Thanos may have just stamped his fingers in a few milliseconds. In a few milliseconds, you might figure out that everything is dust. Who knows? But the idea that nothing that we look at is what it is, or the reality that we see is not the reality that is fun to think about. So this is just kind of going over what I'm talking about in terms of travel time. The first time that the fact that light had a speed limit was known for a fairly long time, even before Einstein. And a gentleman by the name of Romer, who I believe is Dutch, could be German, he was looking at he was mainly interested in the orbit of the moon Pluto around Jupiter. But he noticed that his estimations of when those orbits would begin, as it were, changed based on the time of year, or more specifically, based on where the Earth was in relation to Jupiter. So when the Earth is closer to Jupiter, the light has less distance to travel, and so the point at which Io goes behind Jupiter would actually occur faster, would occur earlier than predicted. About 6 months later or so, when it's further away, the point at which Io goes behind Jupiter, or comes out the other side of Jupiter, that is later than anticipated, later than previously thought. And so here we talk about certain distances. So, like I said before, we use the term light year, but we can also talk about distances called light seconds or light minutes, the distances that light takes in 1 second or 1 minute. So if you were to look at the circumference of the Earth, light can go around the Earth 7 times in a single second. Like I said, from the Earth to the Sun, it's about 8 minutes. To Neptune, it's about 8 hours. The Sun to Proxima Centauri is 4 years, and and you can see the rest. As an interesting we're getting to the point now that we are somewhat seriously contemplating putting people on Mars. And so one of the hurdles that is going to happen is these light travel times are going to play a massive role. To the moon, we're talking on the order of a couple minutes, I think. I haven't really thought about that in a while. Anyway, to Mars, on the other hand, that's going to take months. It's going to take months for radio signals to go from Earth to Mars and back again. So there won't be any communication, like back and forth conversations. There will be a message sent out. After a few months, it will be heard. They will then send a reply back. And so that hurdle needs to be taken care of, or needs to be anticipated when it comes to emergencies or things of that nature. Because if an emergency happens on Mars, or even during the travel time, or a trip there, more than likely they will not be able to get quick answers back from NASA. So those missions have to be fairly self-contained, or what's the word I'm looking for? Self-sufficient, in order for them to succeed. So it's one of the things I don't think that is stressed enough in the public arena. All right. Finally, I'm going to end with, while skipping ahead, these are again also light travel times. the size of the supercluster, the Laniakea supercluster, is 500 million years to go from one end to the other, and light takes 13.8 billion years to go from the beginning of the universe to our eye. So I like to say that Einstein was the one to come up with this. I don't know for certain whether or not he did, and I think if he did, it was actually in the context of a calendar year, but the idea is the same. Again, instead of a scale model of, say, 1 meter to a billion meters, we're going to take the age of the universe, 13.8 billion years, scaled down to a single day. Now, I'm not going to go through each of these stages, but just to give you an idea, let's say the universe began at midnight. About 10 minutes after that is when your first stars and galaxies appear. Prior to that, you either had pure energy pervading the universe, or you had small subatomic particles. It wasn't for another 16 hours before the Earth came into existence. So, around 4 hours, 5 minutes p.m., or 4:05 p.m., that is when the Earth popped into existence. The planet Earth has not been around for even half the length of half the duration of the universe. Most of the universe has been around, or the universe has been around for far longer than the Earth has been here. In terms of life on the Earth, again, you can go through this. You can pause this and look at each individual development. But dinosaurs didn't show up on Earth for another 7 hours? And they showed up around 11:35, and unfortunately they only got about 20 minutes to hang out, do their thing, multiply, be fruitful and all that, before an asteroid came by and wiped them out. So the dinosaurs were only around on planet Earth for 20 minutes in the context of a single day of the universe. When you talk about modern human beings, or let's talk about first Homo sapiens, they showed up a minute and a half before midnight of the next day. Human beings, as we know today, modern humans, or essentially humanity in the beginnings of the Chinese cultures, the Egyptian cultures, that sort of thing, hundreds of thousands of years ago, we're talking about 0.2 seconds before it becomes midnight again. Human beings, particularly quote unquote evolved human beings, have only been around in the universe for literally a blink of an eye, less than the blink of an eye. So not only are we just tiny from a spatial scale, we are tiny in a temporal scale. We are just a smidgen of dirt, a smidgen of dust in a vast universe, which has been here for less than the blink of an eye. Again, you can look at that as we're insignificant. Or you can look at that as we are exceedingly significant. That we are, as far as we know, we are the only tiny bit of dust to have existed for any length of time in the entirety of the universe. And who knows where we can go from here. All right, that's all for today. I will be posting this video hopefully later tonight, and I will be creating the next lecture in the series, Lecture 3, probably in a couple of days. That will talk about the topics of what is science, what can science tell us, and how does science evolve, as it were. Does science stay constant, or does science go through different stages of crises and then revolutions in order to basically keep up with all of the data that the scientists are accumulating each and every day? All right, take it easy. Bye.